All right, second example, we have another find the area. So find the area bounded by, here we have an f of x and a g of x. All right, so we have to keep in mind, what does it mean to be bounded? Well, it means to be surrounded by these two functions, right? Enclosed by these two functions. So these functions must intersect somewhere. So when we graph them, we can see that they do in fact intersect at two places. All right, so of course I have a downward opening parabola, quadratic here with a y-intercept of 2, and I have a linear with a slope of 1. So it's this area that I want to find. And we can see here that f of x is going to be our top function and g of x is going to be our bottom function. And we need to integrate from this x value to this x value. All right? You cannot just look at the graph and estimate that. Right? You can't just say, oh, there's -2 and that's 1. You need to find these algebraically or in some other way to know precisely what that intersection point is. You'll have examples where the intersection is really close to -2, but it's not quite -2. And if you just assume it's -2, you're going to get it wrong. So we have these two functions. We may use a calculator to do those, and we'll do an example like that in just a minute. But here we're gonna work through how I would do this if this was a no calculator problem. Okay, so I want to find the points of intersection. To do that, I set those functions equal to each other, and I solve for x in some way. Right, so all that algebra 2, pre-cal stuff is kind of come back to us. In this case, I can get everything over to the left. I have this quadratic equal to 0, and I can factor and solve pretty easily for that one. All right, I might also have to complete the square or use the quadratic formula, something along those lines. So we find these points of intersection, and once we do that, this is a pretty easy problem. We go, okay, well, we have to integrate from -2 to 1, and we do f of x minus g of x, the top function minus the bottom function. We do that, we find the antiderivatives. We evaluate those at 1 and at -2. You can see that the arithmetic here is a little more involved because I don't have n x equals 0, which usually makes my function evaluations really simple. Here I have to actually do that, the function evaluations at both 1 and at -2. But I do that, I work the arithmetic out a little bit, get some common denominators, and I get 9/2 units squared, or 9/2 squared units. All right, let's take a look at another, a little bit more complicated example. So you can read here, if the curves create more than one bounded region, you have to include both of those bounded regions. And the top and bottom curve may not, but they may change. So what used to be the bottom curve in one interval of x values may become the top curve in another. So take a look at this problem. We have f of x is x cubed plus 2x squared, and g of x is x plus 1. So when we graph that, we're going to see it looks like this. And we're going to work this one on the calculator, so we'll get a chance to look at that. And so you can just generate that on your calculator, get a good viewing window so you can see those points of intersection. So obviously here, this straight line is g of x, and the cubic here is f of x. Now you can see in this interval, in this part of the domain, f of x is the top function. But in this part of the domain, g of x is the top function, right? So we always have to integrate and do the top function minus the bottom function. So we need to find the intervals over which f of x is the top and g of x is the top, right? So we have to find these x intervals, and I'm going to do that on the calculator. I did that on the calculator, just second calc intersect, and I get these x values. So I have 3 intersection points, and I have 3 x values which correspond to those points, and I am going to clearly label these as A, B, and C. All right. So when we actually do the integration, again, we're going to use the calculator to do the antiderivative, or to not really to do the antiderivative, but to do the numerical integration. There's two ways you can do this, really. We can save these to A, B, and C, to the variables A, B, and C in our calculator, which is my personal preference. You can also copy and paste these values into your integral, or you can write them down and type them in. Be careful if you write them down and type them in, that you write them down and type them in correctly, and that you don't round off. We don't want to round off anything until our very final answer. So make sure that you use the calculator wisely and well, so that you get that precise answer. But once I find those x values, I can save those as variables A, B, and C in my calculator. And then this is what's happening in my calculator. I'm going to integrate from A to B this x cubed plus 2x squared minus x plus 1. This is f of x, and this is g of x. Then from B to C, g of x is the top. So here's my g of x, and here's my f of x. And when I do that, I get 2.7655 square units. All right, just so that you can see the way that I use my calculator for this, I would probably label this y1. And in this case, the labeling is really just for me. And then label this y2, and I would put those in my calculator. I did that to see this graph and to find these x values. I want to label them here y1 and y2 so that I remember which one's which. And then when I put it in my calculator, I really am doing this. That's really how it looks when it goes in my calculator. I think there are parentheses in here by default on the calculator. So that's really how it looks when I put it in my calculator. This is what it's actually doing here, and this is the answer that I get, and then I round that off to 3, at least 3, either round or truncate to at least 3 decimal places. I kept 4 here just to be safe.